our presentation of the latches. We have looked at the SR latch with two cross-coupled NAND gates, this is what we have looked at before, and we call this to be the set and this is to be the reset. Now, suppose we send the set and reset not direct to the previous part, but through two other NAND gates, and we put an enable here as the other input of each NAND gate. Let us see what will happen. If enable is 0 here, this will be 0, and this will be 0. And doesn't matter what is R and S, this will be 1 here, and this will be 1 here. And when this is 1 and this is 1, this is a Q prime, and this is Q, 1 and the Q, inverted Q prime, and 1 and the Q prime, inverted Q. So with this, we say that nothing will happen to the latch, no change, irrespective of the value of S and R. So S and R don't care. If enable is 0, the latch will be as S. But let us now look at what will happen when the enable is 1. Let us say enable is 1 here. So this will be 1, and this will be 1, and this will be 1. And if S and R are 0, 0, this 0 and this is 0, 0 and 1, 0, inverted 1, and 1 and 0, inverted 1, again, the latch will have no change, as we can see in this row. If we want to set the latch, we have to make enable 1, and the S is equal to 1. So if this is 1, and this is 1, 1 and 1, 1, inverted 0. So this will become 0. And if this is 0, this will be 1. And this will be 1. And this will be 0. And this corresponds to this row of the function table. Enable is 1. Set is 1. R is 0. Q will be equal to 1. Similarly, if we want to reset the latch, we will make enable 1 and reset 1 and set 0. If we analyze the circuit, we will find that Q is equal to 0. Now finally, if we make enable 1 and S1 and R is equal to 1, what will happen in this case? We have this AND gate has 1, 1, so this must be 0. And this gate 1, 1, and this must be 0. And if this is 0, this will be 1. And if this is 0, this will be 1. So in this case, we find both outputs of the latch are 1s, and we call this state as an indeterminate state or unwanted state or a state that we would like to avoid. So to summarize this part, we can conclude that an indeterminate state or indeterminate condition occurs when all three inputs are equal to 1. Now, it is difficult to ensure that both S and R are not equal to 1 at the same time, and therefore we move to another type of latch. Now, to conclude on this slide, all we can say, this slide, this latch really, we have added one more input, which is called control input. It's called enable or control. So with this enable input or control input, we will control whether the latch will function or will not function. If the enable is 0, nothing will happen. We say that the latch is not enabled or the latch is disabled. And if enable is 1, the latch is enabled and the output will depend on the other inputs S and R, as we have just explained. We move from the SR latch actually latch, which is called D latch, which is a very important latch in the daily life, and we also call it transparent latch for the reason that we will see next. Now the enable that we have just explained stays as is. It goes to two NAND gates, and instead of S and R, we have only one input. We don't have two inputs. We have only one input, which is called D. And D is input to this gate, and D prime is input to the other gate. So that the inputs to these two NAND gates are never equal to 1 at the same time. They are always opposite of each other, which is very important because this avoids the indeterminate state that we have just seen earlier. Therefore, with this latch that has only two inputs, one is the data input, D, and the other is the enable or control input, the circuit ensures that both inputs S and R are never equal to 1 at the same time. The circuit will work as follows. If enable is 0, it doesn't matter what is D. D is don't care. We have no change. If enable is 1, if D is 0, so let's make this 1, 1, 1. If D is 0, this will be 0. This will be 1 here. And 0 and 1, 0, inverted 1. 1 and 1 inverted 0. And this 0 will make it 1 here. And this one will make it 0. So if enable is 1 and D is 0, Q is 0, and we say that the latch is in the reset state. On the other hand, we can show that if D is 1, Q will be equal to 1 and Q prime will be equal to 0, and the latch is in the set state. So simply, if we can look at this in a different way, we can say that when the latch is enabled, whatever D is, Q will take the same value. That's why we call it transparent. So if the latch is in a black box like this here, whatever D is, it appears at the output. If D is 0, the output is 0. If D is 1, the output is 1. That's why they call it transparent latch. Now to summarize, we have described three types of latches, and we present them now with graphic symbols for simplicity. We know what is inside. The first one is an SR latch, which has S input, R input, and one input, which is a Q. The other input is a Q prime. We don't write a Q and a Q prime. We write one with a bubble, which is for prime, and the other one without a bubble. So we have normal output up on the top and complemented output at the bottom. And the latch is designated by a rectangular block. The other latch is the latch with NAND gates only, and the set and reset by logic 0, not by logic 1. Therefore, we write S here and write this bubble, small bubble, and R with a small bubble to say that the reset and set are done by logic 0 and not by logic 1s. Therefore, bubbles and bars at the inputs to designate the complement negative. So we call it S bar R bar latch. The last one is the D latch, which has one data input D in addition to the enable input. Again, two outputs, one for the normal output and one for the complemented output with the bubble. Now, the latches that we said they are very important, they have serious problems. The problem is that the state transition of the latch starts as soon as the clock pulse changes to level 1, which is the enable is equal to 1 as we have just described. The new state of the latch appears at the output while the pulse is still active. Let us explain it with the following block diagram. Suppose this is a circuit that is using latches and the inputs change, and when the inputs change, the output will change. Now, this depends upon what is stored in the latch, as we can see here. Now, this will also change. Now, when the clock pulse becomes logic 1, when it becomes 1, the inputs of the latches have changed, therefore the outputs will change. And this change will be again given as input to the conventional circuit. If the input is still the same, the outputs will change. And so are the inputs to the latches will change. If the clock is still 1, this will change, and this will change, and this will change, and this will change, and so forth. Therefore, the combination circuit will generate new outputs, and the state of the latch will change again and again many times within the same clock pulse. This is the main problem with the latches, and actually we avoid this by not using latches but using flip-flops. I'm sure with this you will really be excited now to know what are the flip-flops.